So, welcome back, everyone. So, in the last lecture, George introduced the whole framework of conformal random growth, the way these models are constructed, the motivation for them. And this lecture, we're going to try to look at one model in particular, look at the scaling limit result for it, or one particular scaling limit, because as George pointed out, there are many different ways of taking these limits. And the aim is going to be to draw out the features of conformal random growth that give us tools we don't have access to in discrete lattice models, and to give you an idea of some of the techniques that we use in studying these. This whole lecture series is, as you know, aimed at early career researchers, so I hope that if you're thinking of going into any form of random growth, you'll consider conformal models after this, and if you are, it will give you some techniques you might want to keep in mind in your own research. So I'll very quickly recap the Hastings-Levitov model, which we'll be using. I won't go into alpha. So we let the particle angles, the attachment points, they are all independent and identically distributed uniformly between 0 and 2 pi. As George pointed out, this means that this corresponds to attaching at a point on the boundary of the cluster selected according to harmonic measure. That is the hitting distribution of a Brownian motion, a random walk released from infinity or just from very far away. We construct the cluster by fixing a particle map from a reference domain, that's the complement of the disk, to a smaller domain. So the disk, the outside of the disk minus the particle. So P is our particle here. And it has this analytic property infinity that it's a scaling and some other stuff, further Laurent expansion. And this C here, the scaling it has at infinity, we call the logarithmic capacity. We can attach a particle at an angle theta by rotating, using F, which attaches a particle at the point 1, and then rotating back. So you can see below an image of the cluster. This is taken from the paper of James Norris and Amanda Turner that I'm going to be discussing today. And the cluster is formed by composing these particle maps. You compose the most recent particle on the right. So that is you attach the new particle and then you distort it by attaching every other particle underneath it. It's a slightly funny feature of the model, but is necessary if you don't want the nth particle. If you apply the nth function to every other function, then the cluster would change shape at every point. It wouldn't be aggregation anymore. It would be, I don't know what you'd call it, but everything would move around at all points. But the cluster is defined as the complement of the codomain, the image of the map. And equivalently, if the map has certain analytic properties, these same ones at infinity, then specifying the cluster uniquely specifies the map just by the Riemann mapping theorem. Because we have the map phi n, it fixes infinity, and it has positive derivative at infinity. This is just what you need to get uniqueness in the Riemann mapping theorem. And so there's a one-to-one correspondence between maps with these analytic properties and clusters. But this correspondence also has respects an analytic structure in some way. We'll go into that because it's one of the many things that makes conformal random growth quite useful. So in a way, it would have been helpful to have something like this in the other slide to answer Dina's question of exactly what is the slip particle. So one of the benefits of conformal random growth is that we have explicit expressions for these maps we're attaching. Well, some of the time. Sometimes we want to work more generally, but sometimes being specific is very helpful. So here, if I want to attach a slip particle, a one-dimensional interval, we have an explicit expression for attaching one to the outside of the disk, but it's kind of complicated. It's a lot simpler to just deal with the half-plane version. And so as you can see, there are these marked points. If I put in either of plus or minus 2 root c, they're getting sent to 0. So these are the pre-images of the base, and the 0 is getting sent to the tip up here. And to get from half-plane maps to maps in the exterior disk, all we have to do is conjugate by the Mobius map between those two reference domains, the outside of the disk and the half-plane. So in fact, if we want to know about the slip the slip map in the exterior disk, all we really need to do is work with this much simpler map. And that's often a trick we can use. It's a kind of a change of coordinates that makes our life a lot easier. So we're going to be talking about convergence limits. So first we should kind of specify what limit we mean. So as George mentioned, there are many different types of limits. There's the small particle limit, where you take the capacity of individual particles C, you send that to 0, and you do something with the total capacity. You can keep the total capacity fixed. That's the kind of traditional small particle limit. We believe there are some conformal growth models where there's a metastable behavior. If you keep the total capacity fixed in the small particle limit, you get one particular limit. But if you allow the total capacity to grow relatively slowly while the capacity of each individual particle goes to 0, you may get a different limit. That's not what I'm talking about today, but it's just something to keep in mind. There's no real canonical choice of which limit to take. You also have George's capacity rescaling limit, which can give you very different limits to the small particle one. But another question we have to ask when we're talking about limits is, in what sense are we converging? So we're talking about clusters. So it's sensible that the set we're working within is the set of compact subsets of the complex plane. So the usual way of talking about convergence of compact subsets of, well, any metric space is the Hausdorff distance between two sets. That is the, if you like, the maximal diameter of a gap between the two, or maximum interval you can fit in the symmetric difference. There are less awkward ways of phrasing it, but the problem is, if I'm going to just show you a quick picture, we need our domains that we're talking about to work in this analytic setting where we use the Riemann mapping theorem and a reference domain. We need them to be simply connected. And this sequence of sets on the left, where you have the closed unit disk and then this section of a circle with only 2 pi over n radians missing, the limit of this is not simply connected. It's not even, well, it's not connected. It's all of this outside the two disks. The limit is all this outside the two disks, union the inside of this disk, but not the circle. So this we're not going to be able to map to it from the reference domain. So the Hausdorff distance isn't the right sense in which we consider convergence. Instead, it's this, which we call the Carathéodory topology on the set of domains. So we can consider clusters, that is compact subsets, or equivalently, we can just consider their complements. And that's perfectly fine because, well, you just take the complement. Convergence of one is exactly convergence of the other. And I don't really want to get into what this definition actually says, but the point is it's technical and it's a bit fiddly. We don't ever really want to work with it directly. I'm just not going to get into it. Look at it and worry. But it does allow us to state a convergence result explicitly. So this is taken from the 2012 paper by James Norris and Amanda Turner, in which they prove quite a few results about the Hastings-Levitov model with alpha equals 0. So this is all the particles have a fixed deterministic capacity and all the angles are chosen uniformly at random on the circle, independently of each other. They prove quite a lot more. In fact, they do prove explicitly that the limit is a disk with respect to the Hausdorff metric as well, but that requires rather more work than we can fit into this lecture, and it's less generally used. In general, what we can and what we do prove is convergence with respect to this Carathéodory topology. So here is the explicit statement. We have Kn, the cluster. Each particle has a deterministic capacity C, and there are n of them. So in the limit, as C goes to 0, with this total capacity nc held constant, the cluster converges to a disk of the radius e to the t, which means a disk of the same capacity. Now, I didn't even want to read out the definition, so proving directly that there is convergence, I guess I also mean convergence in law, with respect to this topology will be awkward. It'd be very difficult. I have no idea how you would go about it. Where do you start with something like that? Well, where we typically start is by turning this awkward geometric question about clusters into questions about the maps. That was the point of bringing in this whole conformal growth setting in the first place, is to be able to talk about maps rather than clusters. So we have something quite powerful from 100 years before this paper, the Carathéodory convergence theorem. So I'm going to state the theorem in terms of the unit disk, the inside of the unit disk rather than the outside, just because it makes it slightly simpler to state. This is all equivalent just by applying an inversion. Z maps to 1 over Z. So S is the set of all maps phi, which kind of correspond to our maps from a reference domain to some other domain. So in the external disk, this would be exactly the family from which our particle maps are drawn. They fix 0, which under an inversion would be fixing infinity, and phi prime of 0 is a positive real number, which is equivalent to this having the behavior f of z is e to the cz plus big O of 1 at infinity. So phi clearly uniquely determines its own codomain, but by the Riemann mapping theorem, the codomain also determines phi. And the Carathéodory convergence theorem says this sense of convergence of domains has a sense of convergence for maps. And sorry, this is meant to say compact subsets of D, the disk. So it says if we have maps, phi and phi n, and the corresponding domains, then the domains converge in the sense of Carathéodory if and only if the maps converge uniformly on compact subsets of the domain. So we've turned a slightly obscure and difficult to work with notion of convergence of domains into a very well-known notion of convergence of maps. Converging uniformly on compact subsets is something fairly common in all kinds of analysis. So now I'd say we do have an idea of how to start proving this. This latter condition that, well, I'll see it on the next slide, we'll restate the result that phi n, its supremum, the supremum of the distance between phi n, and this is the map corresponding to the disk. The supremum of the distance on a compact subset of the domain tends to 0. So this will be enough to prove convergence in the sense of Carathéodory. I say convergence to 0 in probability, so it shows that convergence in the sense of Carathéodory happens with high probability tending to 1 as C goes to 0. So this is exactly the same result we stated before, but now it looks much more tractable. We're talking about maps analytically. We know how to measure this quantity. We could have a go at estimating it. It turns out to require a lot more work, which we're going to see. But at the very least, we turned an almost impossible seeming geometric question into a much more tractable analytic one. This is one of the many things I'm hoping will impress you about the conformal random growth setting. So next, I'm going to get into how the proof of this proposition, and so the overall limit theorem, works. So first, I'll introduce a bit of technical machinery, just because it's nice stuff that we can do in the conformal growth setting and either can't do or find much more difficult in discrete lattice models. And firstly, working in conformal, a kind of continuum conformal setting means we can change coordinates very easily. Now we do sometimes change coordinates in discrete lattice models. Lots of the time, particularly IDLA came up. We mentioned that in the questions from George's talk. And a way that you study IDLA is you kind of change to radial coordinates. You talk about a thin annulus, so that's kind of a radial coordinate, and you can consider is that filled? You can kind of vary over it in the argument. But it takes a lot of work to do that. It's fiddly, it might not necessarily work, but in the continuum setting, you can just formally change coordinates. It takes no effort. So if we have a domain D, then we can put a tilde over it, and this is going to kind of be uniformly used for all sets to mean the pre-images under the exponential map. So if you like, d tilde is the logarithm of d, except we haven't chosen a branch of the logarithm, it's every branch of the logarithm at once. And f tilde is also, if you like, log of f, where f was the map corresponding to d. Really, it's defined implicitly by this condition, which is the same, really the same condition. We've taken the logarithm of the condition we had for the Laurent expansion at infinity. And so here's a diagram of what logarithmic coordinates look like. We've got the closed unit disk with a particle on the left, and on the right, we have it in logarithmic coordinates. I've cheated slightly, they're closer together than they should be, but it's roughly what it looks like. So there's another thing we use, which is extremely helpful, especially for the Hastings-Levitov model with alpha equals 0, which we're considering. So it seems minor. Instead of considering these functions fn, which attach the nth particle, we consider the function gn, which is the inverse of fn, and the function gamma n, which is the inverse of the whole cluster map. So gamma n, it goes from the complement of the cluster back to the complement of the reference domain. And now, why is this helpful? It doesn't seem all that different. But you see here, we constructed phi n by, as George made clear, composing on the right with the nth map. So your particles get distorted. And more importantly, if I were to fix a z in the reference domain, then phi n of z as a process as n evolves, as n goes forward, it's a very strange process. It's got all kinds of dependencies. It's not in the slightest Markovian. It's really nasty. But when we invert it, the order of composition changes. So gamma n is, well, it's gn composed with gamma n minus 1. So in particular, if I take a z, which is in the domain of gamma capital N, and first I apply gamma naught, then to get to gamma 1 of z, I apply a function to it. And this function is chosen uniformly at random from, so all these functions, g1 up to gn, they're independent and identically distributed in the space of functions. And so every single time, z is moving according to an IID distributed increment. Well, not necessarily increment, but what's happening to it depends only on its current position and on a new independent variable. So gamma n of z, it's a Markov process. And it's not, as we always have, a Markov process in the space of clusters. It's a Markov process in the complex plane. And so this lets us say quite a lot about the evolution of points, how they move around. And when we're trying to bound the distance of a point from the distance of the same point evolving under the limit map, so evolving under the map corresponding to the disk, this is very powerful. It lets us say gamma n of z is very close to z times e to the minus t, which is what it would be if we had a disk of radius e to the t. And so the cluster itself must be very close to the disk. We'll see this explicitly later. So let's have a look at how we're going to specifically, well, we're going to use these logarithmic coordinates and the inverse functions to come up with an event on which the cluster converges to a disk. So everything from this point onward is really drawn from one proof in section 5 of James and Amanda's paper. So if you want more details, definitely refer to that. And it has far more results than I'm going to be able to present to you. So this event, omega m epsilon, m is going to be a fixed natural number. Epsilon, I say it's going to be small. It's going to go to 0 as c goes to 0. It's going to be something like the cube root of c times a logarithmic term going to infinity. So something like log of 1 over c. For now, just imagine it's something small. So this first condition, it says that on a half plane, so a half plane in logarithmic coordinates is the outside of a disk in regular coordinates. So this is when the modulus of e to the w is greater than or equal to e to the 5 epsilon. Then phi n, of w on this half plane, phi n has a distance less than epsilon from, well, w plus nc is just the logarithm of e to the nc times e to the w. That is the map corresponding to the disk of radius e to the nc. So this is just the logarithmic version of, if we go back a few slides, it's the logarithmic version of the thing we're trying to say is small. So on omega m epsilon, well, the logarithmic version of the thing we want to say is small. And so it's a matter of fairly simple calculation to show that the thing we actually want to be small is also small. And so if this first condition captures convergence by itself, why do we want to bring in a second condition? Well, the second condition, it involves this Markovian process, gamma n of z. And so that's far simpler to talk about. And in fact, I'm not going to make any attempt to convince you of this. You can either read the paper or check yourself. I think it's a fairly simple calculation that this second condition is in fact, under some reasonable assumptions, enough to show this first condition. So that is, instead of considering convergence of the map from the reference domain to the complement of the cluster, we can consider the maps from the complement of the cluster we have and the cluster we want back to the reference domain. So what does this say? It says on a half plane, and we've shifted by nc because this is kind of the image of the, well, I guess we're in the right half plane, the image of the imaginary axis under the map that we want, the map for the disk, is just the vertical line with real part nc. So we start from there, we go out by a little bit. If we're a bit further away from that line, then the error is less than epsilon. The error between where we actually are under the inverse map and where we want to be. So both of these says that the error, the difference between the map we actually have and the map we want, is small. It's a kind of standard thing to do, since the map captures the geometric properties. So we have this event, omega m epsilon, on which the cluster converges. And so the key proposition for showing that the cluster converges is going to be that this event has a high probability, a probability tending to 1 in the limit. So we put some explicit restrictions on what the particle is. Now this is, this still leaves it very, very general. It could be anything drawn from the family, as long as it obeys these conditions. I've forgotten one extra condition, which says every point in the particle has real part greater than 1, so it all lies to the right of the closed unit disk. So this includes, for example, the slip particle. It includes this particle joined at a point, includes a handful of other things which you might be interested in. But under these very mild conditions, the complement of omega, so if I call omega the good event, the probability the good event fails is bounded above by all of this. And so if epsilon tends to 0 sufficiently slowly, then this whole thing tends to 0. So we're going to prove this. We'll spend the rest of, if I just quickly check the time, we're going to spend the remaining kind of half of the lecture reviewing the proof of this from James and Amanda's paper. And I will try not to get bogged down in the details. If I'm spending far too long on the calculations, then I guess, George, please use your judgment and interrupt me. I'll try not to, though. And I'll try to draw out just the techniques, the major things that we do and how they help us. So let's first have a look at a quick outline of what we're going to do in the proof. So we start by taking this event omega, which, so the thing that makes this sound difficult is we're talking about, if we look at omega, it refers to every point W, or I guess we only want to prove the second part, so every point Z in a half plane, and a half plane is an unbounded set. The thing we want to do really, and this is a kind of fairly standard technique for showing that a function is small, is to show that this function is to kind of find a bound at certain fixed point Z for this function, this difference here, and then to show that it doesn't vary very quickly in Z. So that is, we have certain fixed points at which we know it's small, and everything around them, it hasn't varied much, and so it must also be small. But in a half plane, since it has infinite area, our fixed points would, we would need infinitely many of them. So we can't just apply a union bound. We would have to have some correlation. And correlation in Z is relatively difficult to prove. I'm not certain how much of it we have. So it would be much easier if we could work on a compact set. So that's the first thing we're going to do. We're going to talk about these events omega r, which instead of talking about the entire half plane, talks about a vertical line on which the real part of everything is equal to some fixed number r. And this doesn't look like a compact set, but remember that we're in logarithmic coordinates, so everything is 2 pi I periodic. So really this corresponds to an interval in logarithmic coordinates or to a circle in regular coordinates. So that's the first thing we're going to do. We'll move from talking about an unbounded set to a compact one. Second thing, we're going to not talk in the slightest about phi n anymore. We're going to talk only about gamma n, and you're going to have to either take it on faith or read the paper that that's enough to solve it for phi n. And finally, we take this thing we want to show is small, and we're going to relate it to a martingale. This is common in conformal random growth. You take the difference between what you have and what you want, and you try and relate it to a martingale. You say it's a martingale with some small error terms. In this case, it's actually exactly a martingale, which is comes from the Markovian nature of this gamma n of Z process, which is really specifically because we're in the Hastings-Levitov model with alpha equals 0. If alpha is anything else, you start to get a bit of dependency. So this is the general plan. We're going to restrict these omega r's and then show that this is small by relating it to a martingale. So let's define these omega r's. So we're going to fix, well, we're going to pick our r's to be distance 2 epsilon apart, epsilon being our small error. So for a fixed r, we're going to define n. Well, it's the maximal integer so that this holds. But if you think that applying one of these G tilde maps, it moves everything to the left by, well, if we did converge to a circle, it would be moving everything to the left by exactly c in times c. Well, when the capacity changes by c, it's actually a bit uneven. So we've got this 2 epsilon error. But think of n as being the last time that we can guarantee that this line still lies in the domain of gamma capital N. That's not absolutely 100% true, but in fact, I think epsilon is such that that is true. So think of n as being the last time we can safely apply gamma n and not worry about domains. So we define a stopping time, very common when we want to make an inductive argument, say n is less than stopping time t, and so with high probability, n plus 1 is also less. So TR, it's the minimum of first n, so we can safely say everything inside here is less than capital N. And when does this infimum trigger? Well, it's triggered at n if n is the first integer, so that for something on the line, either z is in the cluster with n particles, which means it's not in the domain of gamma little n. So because of the definition of capital N, we can more or less exclude this possibility. Or its real part under the gamma kind of inverse flow is, well, it started with the real part R. We've applied the map n times, and the map should have moved it to the left by c each time. And so R minus nc is what its real part should be. And if it's moved more than epsilon than that to the left, we will stop the process. So omega r is going to say, until that happens, and we hope that this doesn't happen, but until that happens, in fact, if it happens, then this whole thing fails anyway, if it happens before time capital N. So if this event occurs, then TR must be equal to capital N anyway. TR is really a failure event. So I have failure time. So if omega r is true, then it says that for everything on the line, the error between gamma n of z, that is where it actually goes, versus this, which is where it should go, is less than epsilon. So it is essentially what this omega m epsilon was, only now we're talking about lines instead of half planes. And we say that if all of these events omega r happen for r equals, well, 4 epsilon all the way up to this kind of slightly fiddly calculation here, which is roughly kind of m times c, which should be t, so roughly from 0 up to t, then the result holds for the whole thing. But in fact, we want to bound the error on a half plane. But what is this error? Well, this left is the logarithm of a conformal map, of a holomorphic map. And so is the right-hand side. And so this whole thing is harmonic. And so if we can bound it on a line, which is a boundary of a half plane, then it must also be bounded on the whole half plane, just by the maximum modulus principle. So dealing with harmonic maps rather than just smooth maps gives us a few more powerful results than we get otherwise. And this is kind of one of the several reasons, lack of a Riemann mapping theorem also being one, that this conformal continuum growth setting is a lot harder to define in three or more dimensions. So hopefully I've satisfied you that we now can just happily restrict to this event omega r and show that its probability is high. So I'm going to need to introduce now a few technical details. And I'm not the slightest bit bitter about needing to get technical, because it's something we can do, which you can't do in a lattice setting. So for example, considering a derivative of these particle maps lets us say things about harmonic measure, which we just couldn't say in a lattice model. So we should be very happy that we're now about to get into some awkward looking formulas, or at least that's what I like to keep telling myself. So g tilde, think of it as just the logarithm of g, if you like, where g is the inverse map. It takes the domain minus a particle and sends it back to the reference domain. And it has this kind of analytic property as the real part of z goes to infinity. So back in regular coordinates, that's as the modulus of e to the z goes to infinity. So let's see, we want 3 facts about g tilde, which we'll use. If we center it, so just subtract z off. So we're considering really the difference. What does g tilde do to z? How far has it moved it? Well, this is going to be very relevant in the next slide where we find our martingale. integrating this g0 tilde from, well, we keep the real part fixed and we just integrate over the imaginary part varying from 0 to 2 pi. Well, that's the equivalent of, since it's periodic, really integrating over the whole line, or taking the average over the whole line. And by the Cauchy's integral formula, that just means it's equal to its value at a point in the interior, or at the center of the... It's a bit awkward because we would probably have to transfer back to the inside of the disk rather than the exterior disk, but since its value at infinity of g0 is minus c, the Cauchy integral formula means when we take this integral, we get minus c out. And these two things, I really don't want to talk about them because firstly, I've talked a lot slower than I expected and might risk going over time. And secondly, it doesn't so much matter what these are. What's more important is the fact that we have them. So let's put this stuff to use. And in particular, let's find that martingale because it's going to make our life a lot more pleasant. So again, as I've mentioned, a common technique in conformal growth is to take the map, subtract off your ansatz, and try to relate that to a martingale. Let's do exactly that. So here we fixed an R, and we're really just trying to show that omega R has high probability. So Mn, we're going to define it as the difference between our map and our ansatz. And we just say, not that this is close to a martingale, but that it is a martingale. Well, let's have a look. So Mn, it's gamma n plus 1 plus this. Have I forgotten something? Yeah, there should be minus z somewhere here. But that's all right, because when we subtract off mnz, it's going to disappear too. Well, we get to gamma n plus 1 by applying g. And, well, by applying, sorry, gn plus 1 for the n plus 1th particle. But since that's at angle theta n plus 1, all we have to do is subtract it off this argument and add it on again after. But g0, to get from g to g0, we're just going to add the inside of this back on. So we end up with, firstly, g0 of something minus something independent. This is independent of gamma n. And then we've added on this here, which, if I'd remembered to subtract z off in the first line, would be mn. So the expectation of the increment, well, the only thing left, with respect to this, the filtration generated by the angles up to time n. So the only random thing here is theta n plus 1, which is uniform between 0 and 2 pi. So we integrate over this, and the expectation we get is this integral here, which is what we applied the Cauchy integral formula to. We have this spare c, they both cancel, and we find that we have a martingale. It feels kind of almost magical, but this is really because of the Markovian nature of the alpha equals 0 Hastings-Levitov model. So let's put the martingale to use next. So when we have a martingale, we have access to a huge number of new techniques. In particular, one thing we know is that if we can bound a martingale's increments, then we can translate that into we can use the fact that it's a martingale to bound the martingale itself, or its supremum, much more effectively than just as the sum of the bounds on its increments. In fact, we use the sum of the, well, let's first see what bounds on the increments we have. This is using one of our earlier technical estimates. I said I didn't want to get bogged down in calculation. So what you get is something depending on n, and really doesn't matter what it is. That's just a matter of doing the sums. So I said we get access to a lot of tools since we have a martingale. Here's one of those, the Azuma-Hufting inequality. So for a martingale, xn, if we can bound the increments by something depending on n, then we have the following large deviations result. And you could as easily say the supremum of mod xn over n here. the supremum, the probability that we exceed some value lambda is small as long as lambda squared is more than the kind of sum of squares of these bounds. I guess lambda would have to be more than the square root of the sum of squares. But ordinarily, the triangle inequality would just allow you to add up these upper bounds. Here we can take a kind of Euclidean combination of them, which is much stronger. Well, it can be much stronger if the xn's are small. So we can apply this directly. We've bounded the increments of this mn process, and we can combine it to, and bear in mind here that we've got a fixed z, to bound the probability that the supremum up till time t, or tr, is greater than epsilon over 2. And this right-hand side here, it's a kind of stretched exponential. Since epsilon is, I think I said it was the cube root of c times the logarithmic correction. This whole thing is a stretched exponential, e to the minus kind of log cubed of 1 over c. It decays to 0 very, very quickly. But this was pointwise, as I said. So this isn't enough to bound what we originally wanted, which was the supremum of this error not only over n, but over z. So it's possible that if I fix a z in advance and say how large is this, I'll find the answer not large. But there is still some exceptional point, some exceptional value of z, which will be random, at which the supremum is very large. So next we need to bring in the second stage of this argument. Our first one said at given defined points, the error is small. And the next thing we need to do is say the error varies slowly in z. So we need some regularity result. So the regularity result we're looking for is if in here is the difference between the martingale at z and the martingale at z prime, we want to show that in varies slowly as z goes to z prime. How are we going to show this? Well, it's a stochastic process indexed by z. And so there is a very classical way of, a very classical regularity result for stochastic processes, which says, it's the Kolmogorov continuity theorem. It says that if I can show that the second moment, I'm going to specialize it quite a lot here. If I can show that the second moment of my stochastic process, so kind of the second moment process, is Holder continuous for some exponent, then the process itself, you'll have to do a modification sometimes, but what we have is continuous anyway, so that's fine. Then the process itself is also Holder continuous. So I'm guessing you'll probably know what Holder continuous means. It means we have a bound of this form, z minus z prime to the gamma. So that allows us to pass quite easily from having to talk about the random process I to just talking about its second moment. And again, this is a martingale. Difference of two martingales is a martingale. So bounding the second moment of a martingale is, delightful. It's very easy for us. And I realize I'm about 5-10 minutes behind where I thought I should be, so I'll try to move a tiny bit quicker here. Maybe skip over one or two of the techniques I wanted to show you. One trick we can use is Dub's L2 inequality, which says we can bound the supremum of a martingale on an interval, which is what we actually want, by its value at the end. Very helpful. We can also bound the second moment of the value of a martingale at n to the sum of the second moments of its increments. This is very closely related to the Zuma-Hufting thing we were doing. We do a technical calculation and taking second moments, skipping over quite a lot, we find that Sn is bounded above by the sum of two things. Firstly, of this function here, which doesn't depend on s. It's just we have this factor of z minus z prime squared in the whole thing. So it feels hopeful we're going to get something that we can apply Kolmogorov's continuity theorem to. And we also get something involving the sum from k equals 0 to n minus 1 of sk weighted by this thing. But this looks a hell of a lot like Grunwald's inequality. I don't want to go into this too much, but it's kind of a continuous time version of the same thing. If we have a bound on x, t, in terms of both a function independent of x and the integral of x against some other function bs, some weighting function b, it's like beta, then we can turn that into an explicit bound. We can kind of pretend that this inequality is an equality and solve for a bound. So we can do the same thing for Sn, and after a couple of calculations, we find that this second moment is bounded by something times the modulus of z minus z prime squared, which is lovely, it's what we wanted. And so we apply Kolmogorov's continuity theorem, and we find that for all z and z prime in the line, the difference between one point and the other, the martingale at one point and the martingale at the other, is proportional to the cube root of the distance between the 2 points, multiplied by some constant. And importantly, this constant doesn't depend on z and z prime. It's just, it is random, but it's a random variable completely independent of which points we've picked. And it has a second moment, we know. Let's do a this bit I do kind of want to explain because it's very hard to see how we finish the proof if I don't. So we've shown for given fixed points z that the probability mn of z is large is bounded, it's small. So what we're going to do, since we are dealing with an interval, really, rather than a whole line, we're dealing with the points whose real part is r and whose imaginary part is between minus pi and pi. We can pick L points on that line, and then since we had this upper bound on the probability of exceeding epsilon over 2, the probability that any of them exceed epsilon over 2 is bounded by L times this probability. And so that's the one event. All we need then to show that the whole thing, that mn of z never exceeds epsilon, is that the difference between one of these points, the difference between mn at one of these points and a different point, any different point in between this point and the next, is less than, we need to show that that distance is less than epsilon over 2. So that's exactly what this event says. The distance between the 2 points is going to be pi over L, or really half the distance between the 2 points, because everything has to be pi over L from one of our fixed points. The probability that the error, that the difference is larger than we want it to be, this event looks like it depends on uncountably many things. But because of this universal bound, this bound m that didn't depend on z or z prime, in fact, this whole event can be bounded by the probability that m exceeds epsilon over 2 times this power 1/3, which comes from the 1/3 here. And we know m's second moment. It's pretty much all we do know about m. And so we get this upper bound on the probability. As I said, epsilon is kind of c to the 1/3. So this right-hand side looks unpleasant. It looks like we should be unhappy with it because you've got c divided by c to the 5/3. So you get something tending to infinity as c goes to 0. But fortunately, L was completely generic here. So we're going to be free to choose it to tend to infinity as c goes to 0. So we combine our two events. So as I argued earlier on this slide, the only way that this error can exceed epsilon is if either one of our L fixed points exceeds epsilon over 2, or the difference between one of our fixed points and some other point exceeds epsilon over 2. And we've bounded both of these probabilities. This exponential bound is very small, so we can afford to choose L quite large and keep this left term small. We need to choose L quite large to keep this term small. And I'm not going to explicitly tell you which L gives you the bound we wanted, but optimizing over L does give us the bound we wanted. It bounds the probability of omega r, which is exactly what we wanted. We've proved that this error is small. And so by the correspondence between maps and clusters, the entire cluster converges. So I'm acutely aware of the time, but I will try to quickly recap what we've learned, which is that we have a correspondence between, kind of just purely by the Riemann mapping theorem, we have a correspondence between maps and clusters, but the Carathéodory convergence theorem says we have a correspondence between convergence of clusters and convergence of maps. And talking about maps is in general an easier analytic question than the awkward geometric question. We can compute things explicitly because we know what the maps are, or if we restrict to a class of particles, we know things about the maps. And that's very, very useful. We can't do that in a discrete setting. In particular, harmonic measure is very closely related to the derivatives of the particle maps. We can do kind of formal tricks like changing coordinates. And this is in particular for the Hastings-Levitov model. There's a Markov process associated with the inverse. And so there's an exact martingale. All of this is extremely nice. Things we can exploit, things we know about. And so hopefully that tells you why conformal growth is brilliant. I don't want to denigrate other parts of maths. They're also great. Oops. So the fact we deal with harmonic functions lets us use useful tools from kind of classical analysis, such as we use the maximum principle to say when we bound a function on a line, that's equivalent to bounding it on an entire half plane. So we've gone from a kind of compact-ish, sort of compact in this setting, a set to a non-compact set. We've got martingale theory. Everyone loves martingale theory. Say no more, really. And there's also a lot of room for ingenuity. If you could just follow a recipe to solve any of these papers, then we'd all be replaced by robots. So there's if you have knowledge of other areas of math and you're thinking of doing something about a conformal growth model, you will, I'm not going to say almost certainly, but you may well find clever ways of applying knowledge from other fields. So here there was a very useful application of Kolmogorov's lemma, Grommel's inequality, very popular in stochastic analysis. I'm sure there are many, many more. So I'd just like to quickly thank James and Amanda, whose paper I have followed extremely closely in this lecture, but I haven't done it justice by any means. There are far, far more results than just the one I've talked about, including actually talking about the branching structures of the branches that make up the Hastings-Levitov cluster, which is very interesting. And if you're interested in the Carathéodory stuff, I know that's not something people spend a lot of time thinking about in this field. I would recommend the appropriate chapter in Durham's book on univalent functions. So thanks for listening, everyone. I hope you've taken something away from this talk and that you will, if not necessarily work in this field, it will at least inspire you in your own work. Thanks.
Well, thank you very much, Frankie, for a very nice talk. Does anyone have any questions for Frankie? Okay, if not, I've got one question. So obviously the work here you've highlighted is particularly in the case of alpha equals 0. Could you just talk about very quickly how the method changes when alpha is bigger than 0? Obviously, you need to introduce some regularization, as we've discussed in the first talk, but how does the general method in terms of actually finding the result, how does that change when alpha is bigger than 0? Or does it change?
I wasn't looking for any slide in particular there. I should just close these. But yeah, so really dealing with alpha equals 0, we brush a lot of things under the carpet because the capacities don't depend on anything else. We don't really have to evaluate the derivative of the map. When you bring in positive alpha, we do have to evaluate the map. So you need to make a choice of regularization. And really that choice of regularization brings you into the whole world of different models. You can either have almost negligible regularization like I use, or enormous regularization like you use. It depends on the setting, what's possible. I would say from the little I know about Hastings-Levitov with positive alpha, you do something broadly similar. I'm not really the one to ask here, but I think you would use a lot of the same tricks, or not tricks, but methods of maybe seeking to find something like this ansatz, evaluating the difference. I'm not going to be able to give you a very satisfactory answer. Sorry, I've not really looked into the question, but
okay.
Yeah, I think the real difficulty, I can tell you what would be tricky about it, what would fail in this is you wouldn't have neither this phi n nor gamma n would be a Markov process anymore. The map gn would depend quite strongly on the previous maps or the previous angles. So you'd probably end up seeking a near martingale rather than a martingale.
Yeah. And the other thing I thought might be worth mentioning actually is just what you do, the work you do in your research, because I think that's quite interesting in how it's quite different to these models that, whilst it's still on the models that we're studying here, how it works slightly differently. And don't know if you wanted to talk about that very quickly.
Yeah, thanks, George. So you briefly mentioned in your talk the ALE model in which you can vary the attachment rule as well as the size of particles. So that's the setting in which I work. You have an extra parameter eta. So it's broadly like the Hastings-Levitov model. We have two parameters, alpha and eta. Alpha does the same thing, essentially. And eta controls, so if HL0 uses harmonic measure to decide where you attach, eta decides whether to exaggerate or invert harmonic measure. A very large eta means the areas of high harmonic measure, they get much more attractive for the next particle. And a negative eta means the areas of low harmonic measure, they get much less attractive, and the places that had low harmonic measure you want to attach there. And this is possible because we have, with some regularization, we have a kind of a proxy density for harmonic measure. So you can easily just raise that to some power of minus eta, well, of eta. And yeah, my work has centered on what happens with very strong values of eta. It's kind of based on a paper of Amanda and Frederick Wickland and Sola from 2018, in which they found for very large eta, because once you've attached one particle, the area of highest harmonic measure is the tip of the previous particle. You just attach, for sufficiently large eta, you just always attach to the tip of the previous particle every single time. My work is the same thing for negative eta, in which I prove you always attach to the base of the previous particle every single time. So that's to one of the 2 points either side that corresponds to the base. And through things I don't want to get into, that leads to the scaling limit being a Schramm-Levin revolution, which we were all quite excited by. Current thing I'm working on in the same field is going back to this 2018 result of Amanda, Frederick, and Alan, and looking for metastable effects. So they found that the limit is a one-dimensional line when you take the small particle limit and keep the total capacity fixed. What I want to look at is you take the small particle limit, but you allow the total capacity to go to infinity fairly slowly. And we believe that this gives you a different scaling limit.